What is frequency domain modeling?
It is
Yes.
frequency domain model is when you come up with that create models based on motion, equations of motion.
Modeling of system dynamics or equations of motion. System dynamics are generally equations of motion.
Yes.
As a function of frequency. Okay. And we use Laplace transform for this. Right? Now the other thing you have heard, but not quite figured out, is transfer function. Transfer function is nothing but the ratio of system output. System output is also called response. System output to system input. Again, as a function of frequency. Okay.
The LT stands for Laplace transform.
Laplace transform. We have looked at spring mass damper system. We looked at time domain modeling. And this was as a function of differential equations. And we looked at frequency domain modeling, Laplace transform, and we also looked at impedance approach, right? So just like spring mass damper system, which is a mechanical aerospace system, you can see it as mechanical system. If you're looking at electrical system, electrical circuits. We discussed three components of a spring mass damper system. What are three components of spring mass damper system?
Spring mass, damper.
Spring mass damper. So just like that, electrical circuits also have three components. The three components are, first one is we use this symbol. It's a resistor. What is the relationship you need to know? One is V is equal to IR, right? Or You have to understand here, this R is not a function of time. That is what makes it a time invariant system.
That's what makes it a what?
Time invariant, LTI. We call LTI. Okay. And what is the input? Generally, what is the input?
Current.
Huh?
Current.
You cannot input current. Do you ever input current?
Yes.
Voltage. You change the voltage. You can control the voltage. You cannot control the current. Hmm?
Yeah.
You have to control the voltage. You can always vary the voltage. Current is just based on what is the voltage, what is the resistance. Current will flow. Okay? So, for example, you cannot really control, you cannot push water. Right? When you think about electrical circuits and this thing, you have to think about water flowing through pipes. So, what is the potential difference in when you're talking about water flowing through pipes?
Size.
To think about the potential difference is the height. When will water flow? When there is a potential difference. Energy will always flow from higher potential to a lower potential. So here you have to also understand that voltage potential is potential in the voltage. So current is the flow of water itself, flow of electrons itself. Only when the potential is, there is a change in the potential, water or current will start flowing. This resistance is resistance to the flow. Aju, it's important. This resistance is resistance to the flow. So you're thinking about pipe. If the pipe is smaller, what happens?
Resistance is higher.
Resistance is higher. So similarly, if the wire is smaller, if it's a lower gauge wire, what happens? There's a lot more resistance. The wire gauge is higher, what happens? Less resistance. So similarly, the length. The longer the pipe, it takes much more time for the water to flow. Right? So resistance is also proportional to the length of the wire. So from this, you can say, again we'll introduce this term impedance. Okay? This is the resistance of this resistor is R. The impedance will simply be R. Okay. Here you can think about this as, you want to express, let's use the small v and small I. Okay. V is equal to Ri. You can say this V of t is I of t, or I of t is equal to V of t. Now how do you get this? Again, think about what is the transfer function? Transfer function is output over input, right? So what is the output?
With which one?
So if you think about, just for now, just take this as the impedance. Okay? The next electrical component we'll be using is an inductance. Okay? Inductance is denoted by L. And the relationship between inductance and voltage and current is V of t is equal to L into E I of t over dt. And the impedance is generally denoted by L of Ls. And finally, we have the capacitance. Use this symbol. Capacitor. The relationship is V of t is equal to C into integration of I dt.
And that is a V
Hmm?
up above the one you just said was V. Directly above it. That's V of T as well?
This one?
No, below that. Right there, yeah.
Yeah, that's V of t. Small v, just v. We have inductance. The impedance is 1 over. Now we'll take a look at an example and see how to use this. Take a very simple circuit. We have an inductor. This is V of t. And the current flowing through this would be okay, just like what we did. Now, if you were to apply directly Kirchhoff's voltage law, this is also called mesh analysis. So what you get is applied voltage is equal to. So you have to understand something here. When you apply voltage here, right? All these are in series. What happens to voltage when it is in series?
When you said when you apply voltage where?
This is the applied voltage, and what you're trying to do is this is your input, and you're trying to, let's say, measure. The goal is to measure the voltage dissipated here. Dissipated in the sense? Huh?
Series voltage divides. In series voltage divides.
Voltage divides or it is distributed. Okay. So what you are going to do is V of t is whatever voltage you apply here, input voltage, it will be distributed. Part of it will be here, part of it will be here, part of it will be. Okay. It will be. So this is energy, you are applying energy, right? And then it is dissipated. It's just taken up. So think about it is used here. Whatever you are supplying, this is like a supply, and this is used. Part of it is used here, part of it is used here, part of it is used here. how much of it is used here? Tell me. If we just apply inductance, L, the voltage drop here is L into d I T over dt plus R into RT plus this is 1 over C. So this will be 1 over C integration of okay. So this is tau. You don't really have to take this. It just means you're integrating between a time frame.
So that's just addressing each of the elements that you have on there, all three.
Right. So what this applied voltage is equal to drop in those voltages. Okay. When you apply this voltage, that voltage is used. So that is what Kirchhoff's law says, right?
And this has nothing to do with that current in the middle.
That is. You see the I? I is always there. When in series, the same current flows. Okay, when you apply voltage, the current doesn't get divided. When it's in parallel, the current gets divided, or it gets distributed. Okay. So here, if I were to use the impedance method, what we'll do is, what is the impedance associated with L? LS, right? So we'll simply use this. Let's be like this.
What is the S in it?
Huh?
What is the
S is the frequency variable, Laplace variable. Okay, this is a Laplace. We have talked about this. This is a Laplace. Okay. Just go and review the lecture. I think you understand. What is the impedance associated with R?
R.
Simply R. Okay. What is the impedance associated with C?
The one over C is.
So what you need to do is, again, you have to just follow the same thing we discussed. So this is essentially your equations of motion for this circuit. You are trying to figure out what is the input here. Input is the voltage. Okay. So you're trying to figure out what is the input versus output. Alright. If you're applying this voltage, what is the L is known, R is known, C is known. Those quantities are generally known. Those are properties of the material. Okay. So if you apply impedance approach,
So is the output the current?
output is, now what we're trying to do is, output is actually the voltage dissipated. Voltage dissipated at this, here let's say we are interested in voltage dissipated at this component. Now if you see, this voltage dissipated is only a function of, it's only a function of this current. What is Vc of t? Tell me. This is actually Vc of t. Okay, Vc of t is this. It's only a function of this I, right? This C does not change. In that sense, I is the output. Again, if you are interested in, let's say, the voltage dissipated at this component or this element, What is it a function of? It's a function again of I of t. So R itself is not changing.
So are we saying that I of t, or not I of t, but well, yeah, I of t, are we saying that that's the input? I thought.
But he did mention that the input was the voltage.
Right. This, don't confuse this voltage and this voltage. Okay. This is, you can say, think about this as VR, VL, VC. Okay. This voltage is not the applied voltage. If you apply, what it says is if you apply a voltage across a resistor, this is how much, knowing the resistance of, think about this, if you have something like this, right? And you apply voltage across this V R of t, and you know the resistance. The current flowing is I of t, is given by I of t. You can just multiply, knowing the voltage. If you know what voltage, if you divide the voltage by resistance, this is the current. You'll get to know what is the current flowing. So what this voltage gets divided into V L of t. Okay. What is this voltage? V R of t. This is, you can say, just say this is V C. So when I am writing this, I can also write this as V of t is equal to V L of t plus V R of t plus V C of t.
So the input are those three.
Huh?
The input, excuse me, the input is the V of t, and the output is all of those three.
Yes. So if you were to, what you'll do is you'll figure out, so you think about what is the applied voltage. All these are outputs, right? So there is somewhere you are applying the voltage, applying this voltage. All this gets distributed. So this is all output, what you see. So there is, what is that output? There is a voltage output. There is some power being dissipated. So if you know the current, you know the output. You understand this now better? So the voltage, input voltage is equal to this thing. If you're talking only about this, you will not use a V of V R of t, right? You'll use just a V of t. But if you are applying something like this voltage has to get distributed across. Now what is this V? V L of t is this. Okay. V R of t is this. And V C of t is this. Now if you go to the impedance approach, before taking the impedance approach, if I simply do, if I take Laplace transform, I'm going to get V of S is equal to V L of S plus V R of S plus V C of S. Now V L of S is L S I of S. Okay? V R of S is R into I of S. V C of S is 1 over C S into R. Again, think the Laplace of this. What is the Laplace of L di over dt? Think about what we did. What was the output in terms of when we discussed the spring mass damper system? X of t was the output, right? When we took the first derivative, recall this. We have f of t is equal to d over dt of x of t. What is the Laplace? How do you take the Laplace of this? It is f of s equal to s into remember, just recall this. You are applying exactly the same. Your V L of s is this. V L of t is this. Okay. So we are just expressing this as V L of s. But what is the Laplace of this? L is constant. Since it's di over dt, you get s into I of s. Here it is r into I of t, right? There's only r. R just comes out of it. Here it is. Since it's integration, see there is a differentiation, s is added at the numerator. If it's an integration, s comes to the denominator. What happens if there is a double integration? What happens if there is a double derivative?
You would have added, yeah, you would have added another s.
Yes.
S squared.
It becomes s square, right? If it's a double derivative. For mass, it is s square, correct? So if it was a double integration, this would be c s square
Just on the bottom.
on the bottom, and this is just still remains I of s. Okay. Now, if I just finish with this impedance approach, and you can get one. Impedance approach. We have sum of impedances mesh 1 and equal to sum of applied voltage in mesh 1. So this will be more clear when we do there is an I of s here. This will be more clear when we do multiple loops or multiple meshes, 2-3 meshes. This approach becomes very easy. So tell me, what are the impedances? It is Ls plus R plus 1 over Cs into I of s is equal to, so this V of t becomes V of s. Take the Laplace of each. Okay. And I of t becomes. So here it is. You should not be too overwhelmed with this. This is just voltage expressed as a function of time. This is voltage expressed as a function of frequency. Okay. So here I of s is equal to. If you see this, it's the same as this. You see it? Okay. So transfer function wise, what do you do? Transfer function is I of s over V of s is equal to 1 divided by Ls plus R. So think about what you're trying to do. you know the voltage, applied voltage, you can calculate the current flowing through the circuit. So here, this is a differential equation, right? If you know the applied voltage, you will know what are all the what is the current flowing or what is the voltage drop across any of the components. Similarly, you know. John Lewis, making sense or?
I didn't like it.
Huh?
I didn't like it.
So I just took the output over input. So this goes on the
Okay.
just expressed the transfer function. So if you look at transfer function, ratio of system output response to system input. System output is IFS. We're treating system output as IFS, current, and the system input is VFS.
And how do we know that was one? How do we know that was one? That the current was one? Was
Where's
that,
the current one?
is that one? I thought
Where's
On the
one?
other side?
on the other. Maybe that's not one. I'm looking at one over.
This one? Yeah.
Okay. So aren't you saying that
No, I just did algebra on this.
One over.
If you move the I over underneath D, which you want it the other way around, so you do the reciprocal, so you have to do the reciprocal on the other side.
Okay. So when you point to that transfer function formula over there, we really don't need that. Just take the equation and manipulate it.
No, the system transfer function, this is, you have to express that as output over input.
Okay.
Because you see this IFS is the output. We're treating that as the output.
Just leave the algebra. Okay. Because it may always be there.
John Lewis, got it? Making sense? Quincy?
I need to take a look.
Okay. Take a look. It's not very difficult.